Good evening and welcome to IPA50 webinar series, New Horizons in Physics. As many of you are our seasoned audience, you know that this series is held to commemorate 50 years of Indian Physics Association. We thank you all for the enthusiastic support to this lecture series. Please pass on the word to your friends and subscribe to the channel to keep updated with future activities of IPA. Today, we bring to you another interesting talk in the series, The Crown Prince of Solar Cell Materials by Professor Amlan Pal. And to introduce today's speaker and conduct today's lecture, we have a young physicist, Dr. Satyajit Sahu, who started his research journey under the supervision of Professor Amlan Pal. He was a postdoc at National Institute for Material Science, Japan, and then in 2013, he joined IIT Jodhpur. So I now invite Dr. Satyajit Sahu to introduce today's speaker and conduct the lecture.
Thank you, Professor Nalan. I am grateful for inviting me to coordinate this session. So, good evening, everyone. It is an honor to introduce Professor Amlan J. Pal, whom I have the privilege to work with for my PhD work. What better way can it be than to hear from him on this day of commemorating the 50th anniversary of the Indian Physical Association? Professor Pal has an illustrious career with more than 250 publications and has guided more than 20 PhD students. He got his PhD in experimental solid state spectroscopy from Jadavpur University in 1987, followed by 3 postdoctoral experiences in CNR Bologna in Italy, Abo Academy University, Finland, and Massachusetts Institute of Technology, USA, of Foundry and Forge Technology, Department of Material Science, Ranchi, during 1991-92. He then joined the Indian Association for the Cultivation of Science as a lecturer and continue working there, and where he is currently holding a position of senior professor and J.C. Bose Fellow at the Department of Solid State Physics. Recently, he has been bestowed with the responsibility of UGC DAE Consortium for Scientific Research, Indore, as its director. His research interest expands from the field of organic semiconductors, molecular electronics, to quantum dots and their applications, and lately into perovskites for their electronics and optoelectronic device applications. He has been endowed with many awards and honors in his career, which include J.C. Bose National Fellowship of ACRB DST Government of India, Fellow of Indian National Science Academy, Fellow of Indian National Academy of Engineering, Fellow of Indian Academy of Sciences, Fellow of the National Academy of Sciences India, MRSI ICSC Superconductivity and Material Science Annual Prize. Then he received Ramanna Fellowship of DST. He also received the Material Research Society of India Medal. Then he has been the editor of some of the peer-reviewed journals, including the Journal of Material Science, Materials in Electronics, and part of the editorial board of Pramana Journal of Physics. With this, I invite Professor Pal to deliver his lecture, and the title of his talk is The Crown Prince of Solar Cell Materials, CS3, NS3, PBI3. Professor Pal, over to you.
Yeah, thank you, Professor Vandana Nalal, and also thank you, Satyajit, for introducing me. So, first of all, I would like to thank IPA for for inviting me to deliver an evening lecture on a Saturday. So, I am really thankful to you all, IPA office bearers. So today, this evening, I plan to talk about this particular topic, that is hybrid halide perovskites. So the title is a little different. So the crown prince of solar cell materials, and I will tell that why I call this material as a crown prince of solar cell materials. So as Satyajit said that I am at the moment at Indore, UGCDA Consortium for Scientific Research, and actually this has been my first talk after taking charge of this UGCDA's Consortium for Scientific Research. But most of my talk, as you will find, that it has been done at ISCS Kolkata. So, I mean, since it's a physics association talk, so instead of just having the chemical name NH3, CH3, NH3, PBI3, so let me explain what is it, what does it mean. So it's called methyl ammonium lead iodide. So it's a very long name. So we often, I mean, it's the nickname, what we call MAPI or MAPI. So I will often refer this material as methyl ammonium lead iodide as MAPI, so that things become simpler for you all. So, I mean, what is this particular material? I mean, why is this one particular material is so important that I have chosen one material to deliver an evening talk at IPA? So I'm talking of only one material, methyl ammonium lead iodide or MAPI. So we often jokingly say that, I mean, there are two types of people in the world who understand Venn diagrams and who don't. Of course, I mean, it is true for any other topic. But in the world of researchers who work with materials, I mean, there is, however, only one type of researchers who know about this hybrid halide material as a solar cell material. So it is so important and so popular material that if someone is working on materials, material physics, material chemistry, they all know about this. They have heard this name, that is methyl ammonium lead iodide or MAPI. So that's and moreover, I mean, of course, there are reasons that why this particular material has become so important that everybody knows about this material, because it is indeed now the crown prince of the material dynasty of solar cells. Because we all look forward that it will come as a replacement to silicon solar cells. Because as you know that in solar cells, I mean, all the panels that we see across India or abroad, they are mostly silicon-based material. And apart from solar cells, you will find that this material, I will show you some examples, that this material is in general is a very interesting material because it is being used in other electronic and optoelectronic applications as well, apart from solar cells materials. So let's start from the beginning. That is, I mean, what are the new materials that have been considered for solar cell applications, materials beyond silicon, what I say often. So first, it was inorganic semiconductors, that is inorganic compound semiconductors. I should write compound semiconductors here because silicon is also inorganic semiconductor. So please excuse me. So it should be inorganic compound semiconductors, organic semiconductors or conjugate polymers, inorganic quantum dots, and of late this organic inorganic hybrid perovskite. So just start with these inorganic compound semiconductors. So apart from silicon, you will find that there are some maybe 10% of the solar cell devices are based on CADTEL, what is called cadmium telluride material. And the other material that is being used in solar cells is a CIGS or SIGS, what is called copper indium gallium selenide. And also CZTS, because it consists of elements of earth abundant elements. That is, most of the elements here are very much abundant in the earth crust. So these are the materials that are being commercially used, mostly in cadmium CADTEL and then SIGS. They are being commercially used in solar cells beyond silicon. In the organic semiconductors, researchers have tried many different molecules and polymers like P3HT, which is called poly-3-hexylthiophene, fullerene. So these are the materials that are being used in organic solar cells. And inorganic quantum dots, in the field of using inorganic quantum dots in solar cells, lead sulfide has been used because lead sulfide has a low band gap. So the intention was to trap the NIR component of the light. So that is the reason these lead sulfide quantum dots are being used. And the last part, that is the organic inorganic hybrid perovskite, that is the methyl ammonium lead iodide or MAPI. So that is also That is the next part that I will be talking on. So if we consider the silicon solar cell, starting from the silicon solar cells is the inorganic semiconductor, compound semiconductors, then organic semiconductors, inorganic quantum dots, and then hybrid halide perovskites. So how, as a device physics person, I mean, how we do research, I should tell, because it's a very broad audience here. So as a device physics person, what we do is that we start with a new semiconductor having nice novel properties. And we try to make the materials, characterize the materials, and find a find another band matched semiconductor. So if I find a semiconductor A, and we try to find a band matched semiconductor B that would form a type 2 band alignment with A. So what is this type 2 band alignment? Because in most of the devices, any optoelectronic devices, you will find that you need two semiconductors like PN junction. You all know that you need two materials. So if you find one material, you try to find some kind of band matched semiconductor, which so that it is forms type 2 band alignment. So if I, while going further, let me explain what is type 2 band alignment. So type 2 band alignment, there are different types of band alignments we call type 1, type 2, and type 3. So in type 2 band alignment, the two materials, they form this kind of staggered gap. And we need this kind of staggered gap kind of junctions in most of the devices, especially in solar cells, because if we have this kind of junction like type 2 band alignment, then upon excitation with light, they will have formation of excitons. And because of this special type 2 band alignment, the electrons will move to one material and the holes will move to the other material. That is, the separation of charge carriers will happen in this type 2 band alignment. Because you have to understand the solar cell. I mean, the solar cell is very interesting topic, like a PN junction kind of thing. So in solar cells, once you shine light, you form exciton in the semiconductor. That is fine, but then you have to break the exciton. And breaking exciton means that you have to give some extra energy to break the electron and hole, and then move these electrons and holes to the opposite direction and get current in the external circuit. But everything I have to do without application of a battery or voltage. That is, my device structure, that is the energy levels of the device, of the materials and the electrodes should be such that the energy required to dissociate exciton should come from the device itself, and the force needed for the electrons and holes to move to the opposite direction and then allow the current flow should also come from the device itself, because I could not and I should not apply any voltage. Without application of voltage, we still could get this kind of generate, that is light generation, of course, does not need any voltage, but then exciton dissociation and then carrier transport to the opposite direction. That is, electrons should move in one direction and holes should move in the other direction and then give me current. And then everything should come from the electronic band structure of the two materials and the electrodes. That is the reason we have this kind of band matched semiconductor needed. So all this band engineering of the semiconductor to tune the band diagram of heterojunction is so much important in device physics research. So whenever we form any device, we first need to know what is the band structure of the junction. That is a heterojunction. Heterojunction means that because we are talking of two materials and then forming the junction. So we form the junction and then get all these characteristics. And as a physics person, we try to understand device physics en route to improve device efficiency, because unless we know the device physics and how the device is working, we won't be able to work on the device efficiency. So in perovskite is a very common name, because perovskite name has come from a Russian mineralogist, and it has a kind of a common AbO3 structure, and a large number of metallic elements are stable in the perovskite structure. If there is one kind of formula I will show you later, that Goldsmith tolerance factor is in the range of 0.75 to 1. So you can just imagine, you can take the periodic table, for example, and then try to form this kind of AbO3 structure, and then you get a perovskite, which is a kind of mostly cubic structure. And in solar cell structures, we generally talk of two types of heterojunctions, because I said that you need a heterojunction for any device application, because just one material cannot give any device application. So instead of just two, here we have instead three materials, that is N-type semiconductors, intrinsic semiconductor, and then P-type semiconductor in the form of this kind of structure. It can be, I will explain what is ETL and HTL. Or an inverted structure, what is called PIN structure in the form of HTL, methyl ammonium iodide, and ATL. HTL means whole transport material and ETL means electron transport material. So basically the structure is something like this. So you have one electrode, which I have defined as anode, and a cathode, and then you have three layers, and the perovskite is in between. Here, perovskite is the absorbable layer. So as soon as light falls, you have some kind of electron hole formation in the perovskite. And because of the band diagram, as I said, that we have chosen the P-type material and the N-type material in such a way that they form some kind of type 2 band alignment at both the interfaces, and because of this type 2 band alignment, charge separation will occur, and the holes will move towards one electrode and electrons will move to the other electrode and give you current in the external circuit when you just contact with the wire. So everything just happens without application of a voltage. So that is the structure that we form in the laboratory with whole transport material and electron transport material along with the perovskite structure, perovskite layer. So that is done in the lab. So when we talk about, so this was the example of a perovskite structure, which I have defined as AbO3 structure. So then we move to hybrid structure, that is hybrid halide perovskites, where I have the, halide structure, where instead of oxygen, I have the halogen. So that's why it is called halide perovskite, because I now have, instead of oxygen, I have chosen X, that is the halogen. So like cesium tin iodide or cesium lead iodide. So these are some examples of halide perovskites. And then next come hybrid halide perovskite. First, I should explain that why we call this material as hybrid halide perovskite. It is the same structure like ABX3 structure, and A is a monovalent organic cation. Remember, it is organic component, moiety now, and B is a bivalent metal, so which is inorganic, and X is of course halogen. So in such a case where you have ABX3 structure with A as the organic and B as the inorganic, so that means that it is neither organic nor inorganic, so it's a kind of hybrid. So that's why it is called hybrid halide perovskite. So as the name comes, that hybrid halide perovskites, that is our MAPI or methyl ammonium lead iodide. Now you understand the methyl ammonium lead iodide, this methyl ammonium moiety or component, it is like A, lead is like B, and A is of course, X is of course the halogen, that is I in iodine. So that is the reason it is called hybrid halide perovskite, and that is the crown prince of solar cell material. There are other examples in this class like permanium lead iodide and so on. I talked about that. I mean, this particular group of materials, they are useful also not only for solar cells but also for other materials, other applications like LED materials, light emitting diode materials. Instead of just iodine, if you try with bromide or chloride, then you find this material to be application, the materials to be applicable in light emitting diodes. Or you can even get field effect transistors with 2D perovskites and so on. So this is not, so the application of hybrid halide perovskites is not limited to solar cells, but it also is useful in applications like LED materials or field effect transistor materials. So how the structure look like, or this organic inorganic hybrid halide perovskite, that is ABX3 structure or methyl ammonium lead iodide. So we have this organic component, that is a methyl ammonium, which is a monovalent cation, which sits at the center. And I have this, I just go another slide. Yeah, so each B side, that is the lead side, is a 6-fold coordinated with the oxygen. So I have BX6 octahedra, TBX6, and they are formed like this. And there is a kind of cage in this cubic structure. And in this cage, I have this methyl ammonium cation sitting there. And interestingly, the size of the cage is just good enough to put this methyl ammonium cation in the cage. Not only that, it can rotate inside the cage of this 8 PBI6 octahedral. So everything is important. I will show you later that even this rotation of rotation of methyl ammonium cation in this cage, that is the size of the cage is so optimum that it allows the methyl ammonium cation to get rotated inside the cage. So everything is important in this particular material. Some of the mirror picture. So I have lead, iodine, and then in the middle I have the methyl ammonium. So at the cage. So what are the beautiful properties for solar cell applications we have for methyl ammonium lead iodide? I will show you that why they are structurally stable, why its optical properties are so suitable, solution process, because I will show you that this material can be made in the lab through solution method, and it has very low exciton binding energy. And as you now understand, I will again explain that binding energy means that I will be able to dissociate the exciton, or charge separation should be much easier. High carrier mobility, because of course, I mean, I need the mobility to be higher, because otherwise, even if I can dissociate separate the charge carriers, I won't be able to take them out. Defect tolerance, because since the material is prepared in the solution method, there are a lot of defects formed, but still we will show that these defects, they do not perturb the conduction mechanism. And most importantly, the low recombination loss, because the main problem of solar cell is that you can of course generate excitons or electron pair and then dissociate them, but they don't like to be separated.
What happened? Dr. Amlan, we lost you. I think you got muted and you lost your screen share.
Okay, now yeah, I stopped because there was some kind of some problem here. So
okay.
from which slide should I say? This one?
Yeah, restart. Yeah.
So I just have to share the screen again. Now, is it okay now?
Not yet. Not shared yet. No issues. You just yeah. Okay, now it's coming.
Okay.
Yeah.
Should be okay. Is that okay?
Yes, fine. Perfect.
Vandana, is it?
Yeah, it's perfect.
Yes. Okay, so I was talking of different properties of methyl ammonium lead iodide, like I mean, why it is structurally stable, why it has suitable optical properties, and why it is, I mean, it is solution process, because most of the large area devices we need solution processability, otherwise we cannot go for large area devices. And then low exciton binding energy, that is the charge separation should occur very quickly without much effort of energy. So I need to separate the carriers. So that is the low binding energy. And also I need to extract the carriers very quickly. So I need high mobility. And we also need about defect tolerance, because these materials are being formed in the solution process. And of course, in the solution process, it's not perfect single crystal, of course. And so there are a lot of defects. But thankfully, these defects, the energy of the defects, are not disturbing the carrier transport. And finally, the low recombination loss, because even if you separate the charge carriers, the most likely event of the separated charge carriers is that they try to recombine and they just give you light or non-radiative recombination way. So this recombination must be minimized, because unless you minimize the recombination, then no device will succeed. So I will now just go through one after the other that quickly, that how one can make this material, why this material has become so important. Structurally stable, like you need band engineering because you need to change the material in for many devices. So whatever you do, like halide engineering, means that you play with the halogen site or substitution at the methyl ammonium site, or even the substitution at the lead site. Whatever you do, you find that the material remains structurally stable. What are the factors what we look for when we check whether that material will be structurally stable? We look at Goldsmith tolerance factor or octahedral factor, which are derived from the effective ionic radius of the elements. And they are the indicator that whether the material is structurally stable or they are under distortion of crystal structure. And these are the just standard formula for tolerance factor and the octahedral factor. And a stable perovskite structure, it is known, it has been told, it has been there, that it should be the tolerance factor should be within this range and the octahedral factor should be within this range. And for methyl ammonium lead iodide, the values are well within this two range. More importantly, if you vary, if you just try, I have just taken it from the internet, that if you try many different such perovskites, methyl ammonium lead iodide group, you find that tolerance factor and the octahedral factor both lie within that domain, that is within 0.75 to 1, and then the octahedral factor 0.44 and 0.90. So whatever you do, that is you do halide engineering, you do metal substitution, or you play with the organic side, you find that they are structurally stable. And its optical properties are beautiful. Like the first thing for those who work on solar cells, they start with the Shockley Queisel limit. So that's the theoretically predicted value. That's the max efficiency that you can get from a single p-n junction, depends on the material's band gap. So it's a very old paper, 1961 paper. So that's the reason that, I mean, you try to get some materials in the 1.23 kind of value, that is silicon, because it has the possibility of getting the highest value. If you try a material like 2.5, you know that you can never get more than 10% efficiency. So that is what we call Shockley Queisel limit. So where do our crown pins stand? Like this is silicon, as you say, that as I have said, that it can really go up to 32 or 33% of value efficiency, because that is its band gap. And then CIGS or cattail, these are the materials because they lie within this range, so that the values can be high. And the perovskite is somewhere here, 1.55. So it can really go up to nearly 30% or 28%. So that is the highest value it can theoretically achieve. And then if you play with the band gap, that is if you can still lower the band gap of the perovskite material through band engineering, it can still go higher in value. So perovskite is not really bad material in that sense, in terms of band gap, that it is not above 2 EV or something. So it is really well within the domain where we have all the big shots like silicon, cattail, and CIGS and other things. So the band gap is really very much within this optimum value of 1.34. And more other thing is that the band gap, this is the advantage over silicon, because silicon has an indirect band gap, is an indirect band gap semiconductor. And that is the reason you need a thick silicon wafer to absorb enough solar light to produce electricity from the solar cell. You need about 300 to 500 micron of silicon to absorb solar light, because its band gap is indirect in nature. Fortunately, the band gap of methyl ammonium iodide is direct. So that means that you need, of course, I don't have to explain that what is direct band gap semiconductor. So you need very little material for this, for the very little methyl ammonium iodide material to absorb enough solar illumination. You can find that you will need only 200 to 300 nanometer thick material to absorb enough solar illumination, as compared to we needed 300 to 500 micron of silicon solar cell to absorb enough light. So that is the advantage, that the optical band gap is direct in nature. So that is at the R point, so they are in the same point of the case space, the conduction band minima and the valence band maxima. And another important factor is the high extinction coefficient, because optical absorption depends on the apart from the band gap, it is also dependent on the extinction coefficient. And because of this nature of the conduction band and the valence band, it possesses very strong, a very high extinction coefficient, and such a composition basically occurs because of the PP transition between the band edges. Solution processability, that is the other part, that is you can make in the lab this particular material. So there are two methods, what we call the one-step method and the two-step method. So thin films can be fabricated by a range of solution-based approach, single precursor, sequential adsorption, and so on. And because of the simple solution processability and unusual defect physics, which I will explain later, we can find some kind of sweet spots. That is, these sweet spots will give me very high PP efficiency, photovoltaic efficiency in structurally stable material. Just a little how we make it, because to be a device physics, I cannot just rely on materials or the thin film fabrication of others. So we have to do it in our lab. So what we do generally in the lab, that is, you just mix lead iodide and methyl ammonium iodide in DMF. DMF is dimethyl formamide. You mix it, then spin it, anneal it, you get methyl ammonium lead iodide film. A little different approach is two-step method, two-step or sequential deposition approach, where you first deposit lead iodide in DMF thin film through spinning method, then methyl ammonium iodide in IPA. IPA is basically isopropyl alcohol, so which is you use it in these days sanitizer. So use it in sanitizer, and then you just spin it. You again anneal it. You get the methyl ammonium lead iodide. So it's a simple lab-based approach, and that is the way it is working. And I said about this materials engineering, you change the I side at the iodine side, or at the methyl ammonium side, or at the lead side. By doing this kind of solution materials engineering, you can vary the band gap. As you can see here, the normal is absorption plot, the normal is PL here, and absorption, that you can vary the band gap of the material by simple solution processing and the materials engineering. I just have given some examples of indium at the iodine side, at the methyl ammonium side, and also at the lead side. So you can vary the band positions, the conduction band or the valence band of the material, and then you can do all sorts of materials engineering and band engineering. Let's talk about this low exciton binding energy. This is very interesting because, as I said, this PN junction, you will have this kind of electron holes pairs, and you have to dissociate them. And how we can dissociate them? That is, we have to just, in this particular material, methyl ammonium iodide, it possesses a large dielectric constant. And because what happens if you have the material has a large dielectric constant? Just remember that Coulomb's law. Because of the large dielectric constant, the electron hole pair attraction, the attractive force will be less now. And because of this less force, it will be easier to dissociate or separate the charge carriers from between these electrons and holes. They are as low as 10 to 50 milli-electron volt. If you think of the room temperature, so often you will find that the material can itself separate the charge carriers within the methyl ammonium lead iodide. And because of this, because of so low binding energy, now the electrons and holes, the electron and hole pair, they have a very weak Coulomb interaction, and they reside in different molecules. That is, they form some kind of what we call Warnier type of excitons. Because of the low binding energy, the electrons and holes, they reside in different molecules, and instead of intramolecular recombination, we need intermolecular recombination, because since the electrons and our holes are residing in different molecules, so for recombination to occur, this intermolecular recombination should be the process for recombination instead of intramolecular recombination, because if the electrons and holes were residing in the same molecule, they could have just recombined very quickly because it's an intramolecular process. But now, since the electrons and holes are separated away from each other, because of that, then we need intermolecular recombination for the non-radiative recombination process. Okay, so next is high mobility or ambipolarity. So, sorry about that, yeah. So, more than that, we have this kind of mobility is high, and it is also ambipolar. That is, the electron and hole mobility are more or less similar, like 200, 2800 and 9400 centimeters square volt per second. So, and the material has high mobility. So once I will be able to separate the carriers, they will be able to move to the opposite electrodes very quickly without any hindrance. And just skip a little, yeah. And the defect tolerance, I said that, of course, since we are making the material through solution process, the material is prone to contain a large number of defects. And but fortunately, the impact of these defects, they does not affect the functional properties of the material. Why? Because depending on the stoichiometry of the molecule, of the precursors and the activation energies, self-doping can be done. And because of that, yes. So because of the strong influence of spin orbit coupling, SP coupling here, the valence band maxima. So the defects, they often give you extra energy levels, and this defect energy, the valence band maxima, is now pushed to a higher level, and the conduction band minima is pushed to a lower level. So the defect states now become lower than the valence band. So as such, the defects, they have some kind of energy like this. But because of this SP coupling, the valence band is pushed upward. So the defect bands remain, defect energies becomes lower than the valence band. So since the defect levels are now lower than the valence band, these dominating donor type vacancies, and so these defect levels which promote the non-additive recombination of charge carriers, shallow levels make the material more or less defect tolerant for carrier transport. That is, the defects are there, but defects are kind of inert. They do not take part in the conduction process at all, because now they are below the valence band in this case. That is, they are somehow inert, and they do not have any adverse impact on the carrier diffusion length or the carrier lifetime as well. And this is in contrast to other conventional compound semiconductors, where the non-radiative recombination is high due to formation of defects within the band gap. Because in this CZTS or CIGS materials, the defects, they form within the band gap. And as soon as the defects form within the band gap, the transport of holes the carriers will become trapped. Or if it is below the conduction band, the carrier will be trapped at the defects, and then carrier transport will be stopped. And but fortunately, in methanolamine daytide, the defects lie below the valence band in most of the cases. That's why even if there are so many defects, the defects, they do not take part in the conduction process. The last part is the low recombination loss. So it's very important part, which I will explain a little more. Because as I said that in any solar cell, of course, you can separate charge carriers, but as soon as you separate the charge carriers, they immediately recombine, and they do not go towards the opposite electrode. But thankfully, in this material, the recombination loss has been found to be very low. Why? That is really some wonder thing. That is why this material recombination loss is so low. Because in spite of the films being formed through crude solution process route, the recombination loss is very low, because it's not any high value or any ultra clean environment that we do. You just make it in the spin coating method, still you find that the recombination loss is low. It is as low as 5 orders of magnitude lower than the predicted Langevin limit. And the carrier lifetime is long, and the carrier diffusion length is large because of that. So why there are now, this is the present research, there are debates about the researchers about the origin of such a low recombination loss or recombination rate. There are several models that are going on: ferroelectric domains, screening of bandage areas, formation of large polarons, photon recycling, defect tolerant nature, then pressure driven structural change, charge localization by thermal effect, and Rashba effect. That is Rashba band splitting. We have been recently working on we have worked on Rashba band effect, Rashba band splitting, and then I will explain that how this Rashba band splitting can explain this low recombination loss in methylammonium lead iodide. So what is Rashba effect? Rashba effect says that, I mean, it's a kind of K-dependent spin splitting of the conduction band and valence band, any of the bands, any of the band magnetic extrema. That is it is said that the conduction band or the valence band, it can be, I mean, they are split. I mean, they are spin split basically. And the model here is that and the origin, let me just tell that why this Rashba effect will occur at all in methylammonium lead iodide. Because we now have a large spin orbit coupling because of high Z element, that is lead. Lead and iodine both are high Z element. So we have a large spin orbit coupling and lack of centrosymmetry arising out of the tilted PBI6 octahedra. We talked about the structure, and they are this PBI6 octahedra are tilted. So there is a large lack of centrosymmetry. And because of this, there is a kind of effective magnetic field, and thereby the lifting of the Kramer's spin regeneration of the electron. And because of that, it is believed, it was theoretically proposed that the bands will be split, spin split. That is, both the conduction bands and the valence band will be spin split. So once the electron and holes are separated, it is now possible that the electron and the hole are residing in states which are where the transition is spin forbidden. So that was the proposal. But theoretically, it was also proposed, no, I mean, they will lie in the spin states. I mean, there are two models. I will just show you the two models first and then come back here. That's the spin forbidden transition model. It is said that the conduction band and valence band, having the different type of spin textures, reside closer to the Fermi energy. Because I said that the conduction band and the valence band, they are now spin split. Now, what is the spin state of these two? Because finally, electrons will reside at the low state of the lower of the two conduction band, and the holes will reside at the higher of the two valence bands. So it is now important to know that what is the spin texture of this conduction band and this of this valence band. So there is a quantum model which says that it is a spin forbidden transition model. That is, the conduction band and the valence band, they have different types of spin texture. They reside closer to the Fermi energy. Hence, a recombination between the electron in the conduction band minima and the holes in the valence band maxima, it is a spin forbidden process. So since it is a spin forbidden process, we get low recombination loss. So that is the first model, what is called spin. They are all models. And there is another model also, where it says that this conduction band of the two and this valence band, they have same spin texture and recombination should be possible. So pictorially, so these are the two models that, I mean, this is the spin allowed transition model. It's been forbidden transition model, where it is said that they have different spin textures. So spin textures are shown in this way. One is this is the anti-clockwise direction, and this is the clockwise direction. So it is so this is clockwise direction and this is anti-clockwise. So transition is not possible. That the other model says that no, it is possible. So that was the two models going on in this in methylammonium lead iodide. So we decided to work on experimentally to know the spin states of the Rashba band split bands, because there should be Rashba band split in this material, that is well known. So only thing that was not known was what was the spin texture of the lower of the two conduction band and lower of the two valence bands, whether this model is valid, that is a spin forbidden transition model, or whether the spin allowed transition model is valid. So we did this work with the spin polarized canine spectroscopy. That is, we have taken the material. I can just briefly tell that. So we have taken the material where I know that there are two conduction bands and there are two valence bands. We brought one spin polarized tip of a canine STM. So this spin polarized tip will now have a particular spin of electrons. That is, this tip will be able to inject only one type of electrons. So now, if this is the model, if this is Rashba band splitting, then this spin polarized tip will be able to inject electrons if it is spin matched or here. So depending on which one is matched, or similarly, if in case of valence band, we will be able to withdraw electrons from either of the two states, because now this tip can accept or give spin matched electrons only. So that is the basic experiment that we did here. So sorry, yeah. So let's see that what we get in case of Valentine spectroscopy. We just get density of states, and then we measure, we get the peak here for the valence band and the conduction band. That is we get the first peak as the where we can give an electron to the conduction band, or this peak tells me that where I can withdraw an electron. So this STS measurement tells me the location of the conduction and valence band. And since it's a very extremely localized mode of measurements, we do the measurements at many different points and then plot a kind of histogram of the two energies, conduction and valence band, and we get finally the conduction band and valence band. So this is without any spin polarization. So I get only one conduction band and one valence band. Now the interesting part is that what happens if I use some kind of ferromagnetic tip, that is if I now inject only one type of electrons, then I find that I get two types of density of states. Either I get two DOS, I mean one DOS with the conduction and valence band somewhere. I should just show you here itself. Either I get these two levels, or I see the away levels, something like this. So at some points I see only these two levels which are closer to the Fermi energy, conduction band and the valence band, or I see the bands which are away from the Fermi energy. That is, this tells that these two states, that is the Rashba band split, these two states, they have same spin texture, and these two states have the same spin texture. That means that if these two states have same spin texture, then spin allowed transition model is valid. So recombination should be possible. Then still we got so low recombination loss. Why it is? That is, I mean, the plot is something like here. So with platinum iridium tip, that is non-magnetic or non-ferroelectric tip, so we get only one level. But with the ferromagnetic tip, we see the Rashba band split. We see both the states here and both the states here. And this red color means one type of spin, the blue colors means other type of spin. So as you see that the inner of the two states, they have similar spin state, and where the outer of the two states, they have again same two states. This means that this model is actually valid. So it is spin allowed transition model. So it should be then recombination should be possible. Then we talked about the domain. So because we got two types of states. So why did we see these two types? We found that if we do one measurement, we get these red levels, and in the next molecule, we see the blue levels. That is, the molecules have just the domains are just molecular in nature. So that is best viewed if we do some kind of imaging. So if you look at this imaging, and this is the scale here, as you can see, is 20 nanometer scale. So that's the DIDP imaging. So this tells us about the domain of the molecules here. So this means that the molecules form domain, and because of this domain, as I explained that, because of the Warnier type of exciton, the electrons and holes reside in different molecules. So now intermolecular recombination needs to be possible, but although it is now some kind of spin allowed transition, but the recombination should happen between two molecules, that is neighboring molecules. And that is the reason I just show here one picture. Just a moment. Yeah, here. So I have one domain. So that is one molecule. I see this JZ equal to plus substates are closer to each other. I mean the conduction band and valence band. But in the next molecule, JZ equal to minus substates are closer to each other. So since intermolecular recombination has to occur in this molecule instead of intramolecular recombination, so this electron must try to recombine with this hole, but that is not possible because they have different spin textures. Similarly, the electrons of this domain should try to get recombined with the holes of this domain, which has a different spin texture. Again, this is not possible. So inter-domain spin forbidden transition occurs, and that is the reason we get this kind of low recombination loss in methylammonium iodide. That is, we showed that yes, this Rashba band splitting occurs in methylammonium iodide, but because of the Warnier excitons and the electrons and holes residing in different molecules, because this electron must try to get recombined with this hole. But unfortunately, rather fortunately for us, that this electron has a different spin texture than the whole of this the spin texture of the hole. Similarly, the spin texture of this electron has a different, this hole has a different spin texture, so they again cannot recombine. So that is what we have done work on Rashba band splitting in methylammonium iodide. So I now conclude that, we have highlighted the prime properties of methylammonium iodide for its success in solar cells. It is indeed rare to find a single semiconductor possessing all such favorable properties. I listed so many properties, and you will find that it is really rare to find all such favorable properties. And we have successfully employed spin polarized kinetime microscopy for the first time to probe Rashba band splitting in methylammonium iodide, because this Rashba band splitting gives rise to splitting and then low recombination loss. And this low recombination loss was considered to be very important for solar cell applications. As I said here, a low recombination loss has been explained through a spin forbidden inter-domain transition model. So with the possibility of further improvement, researchers around the world now eagerly wait for the coronation of the methylammonium iodide to the throne of solar cells. That is, it should and it is going to replace silicon solar cell in future. So I acknowledge my students at IACS. So this work was mostly done by Shomo Chatterjee somewhere at the back there, and then Salma Khatun here, and then Abhishek Maiti somewhere here from Jadavpur. So these are my group at ISCS Kolkata. I thank JC Bose National Fellowship for the funding, Nano Mission Project for the funding, and I again thank you all for your kind attention. I stop share now.
Thank you very much, Professor Pal, for your such interesting talk and informative talk. Now the floor is open for some questions. I can read some questions from, I think, YouTube.
Yeah,
chat
please.
section. Yeah. So, yeah, the first question that I can see is by Avinav Chaudhary. And his question is, what is the power conversion efficiency of methyl ammonium lead iodide solar cells?
So the record efficiency is now 25%, 25.6 or some percent. So that's the record now value. So it is the first material that the efficiency could beat that of silicon. So that is the best thing, because.
Okay. So the next question is again by Abhinav only, and it is CS3NS3 PBI3 or CS3NS3 SNI3, which is better and why?
SNI3 is a little unstable compound, because tin in its two states is not a stable part. It always tries to become SN4 plus. So that is the reason it's not a stable compound. Because it will immediately become SN4 plus. That is the reason SN4 plus, because that was the first try to replace lead, because lead is a toxic element everybody knows. So everybody tried to replace lead by tin, but that was not successful. But again, I have to remember that I need Rashba band splitting, so I cannot forget about the high Z element. I need high Z element at the lead in terms of lead, because if I reduce the Z of the metal, then the Rashba band splitting will not be there, and there will be a lot of recombination loss. So everything is correlated. Everything is correlated in this material. That's why I always say that it's really a wonder material.
Okay. And the next question is again by Avinav. How ferroid domains regulate photocurrent in single crystalline CS3NS3 PBI3 films self-grown on FTO or TiO2 substrate?
Yeah, I mean, a lot of work is going on ferroelectric domain, but that's a little elaborate. So maybe I skip this question at the moment because then I have to really talk a lot about this ferroelectric domain. But I mean, there are reports. I mean, he can write. I can send some papers on. We are also talking on that.
Okay, great. So now Rabi Chinnappan is asking, would MAPI replace silicon? If not, why?
Yeah, because now, and we hope so, because now MAPI panels are already there. I mean, at Singapore, they have already made solar cell panels based on methyl ammonium diiodide. So we really hope that this material will be able to replace silicon at one day. Maybe if not 100%, but at least, I mean, to some extent, it will definitely become, because it has a much higher efficiency than even silicon now. But I try to give this talk from the physics point of view, that why this particular material is so important. So I am not a technologist in that sense that we work on, but I mean, I know that there are panels, solar cell panels based on methyl ammonium diiodide.
Next, it is Hussein. I think his question is, what is the safety factor with lead?
Well, I mean, there are a lot of issues, but so far, uh, if you use lead in devices, since it's a solution process method, so it is still okay, because people are trying to replace lead, but it is very difficult to replace lead at the moment. So far, researchers are still working on lead.
Okay. And the next question is by Basavraj Kagali. What about the cost factor of MAPI? Is it stable, or is it stable to weather conditions?
The initial work, when these methyl ammonium diiodide solar cells were fabricated, of course, there were issues with the stability in terms of moisture and humidity, and then oxygen sensitivity. But now, I mean, there are methods to deal with these stability issues. So there are groups, a lot of workers who are working on the stability aspect, and that is the reason the solar cell panels based on methyl ammonium diiodide is possible, has become possible.
Okay. Next question is by Prem Goyal, and he's asking, how user friendly are these cells? Can they face dust, etc.?
Yeah, more or less similar question as the previous one. Because it's a vast subject, those who are working on stability aspects, they are really working on that aspect only, and because of that, because of course, I mean, dust aspect is actually a little different, because that is also applicable to silicon solar cell. Because if you place the silicon solar cell, if dust falls on it, of course, its efficiency is good, will become low. That is also true for perovskite solar cell, because if you in your panel there are a layer of dust, of course its efficiency is going to become low. But that is not the problem of the perovskite, it is the problem of all solar cells and the dust.
Okay. The final question is by Udit Chatterjee. What is the present status in India for perovskite solar cells?
There are several groups working on perovskite solar cells. uh, I mean, I can name some institutes, but I mean, very active researchers are there who are working on different aspects of solar cells. I mean, considering making the new materials and device fabrication, because all this work, as I showed you, that it can be done in an Indian lab. That is, you can make the material, you can fabricate the device, you can characterize it. Everything is done in the lab under actually one roof, I should say. That all the device results that I have shown here today. We also work on devices. I did not show you the IV characteristics per se, but we also make devices and then do the measurements. But everything we do under one roof. That is, in one room, we make the material, fabricate the devices, characterize it, and we get dark characteristics and light characteristics under light. Of course, I mean, it is a thriving field in research in India.
Okay, so these are the questions from the YouTube chat section. Now, if there are any questions from the audience in Zoom, they can go ahead and ask questions.
Yeah, can I ask something?
Sure,
please.
Yeah. So when you are talking about this Rashba effect and you are saying the two close by molecules have different spin textures, what is the probability that the two conjugate molecules will have different textures? It's also
No.
possible that they may have similar ones. And
No,
then,
I mean, of course, I mean, that is experimental validation, because when we did this DIDV mapping, so what is DIDV mapping? It's a little elaborate, that's why maybe I explained a little lesser way. So in DIDV means DOS. So I am mapping the material, not MAPI, not MAPI. I am mapping the material from the energy perspective. So that means that I am looking at the, say, conduction band of different points.
you're looking at the
so
overall effect, yeah.
overall, so in the film, I am just measuring the conduction band, and then finding that at one point I have the lower, this is my conduction band, and in the next point, this is my conduction band. Similarly, at one point, this is my valence band. In the next molecule, this is my valence band. So that is the reason that we said that the domains are molecular in nature. That is, if in one molecule these are my one particular spin, in the next molecule these are my other the molecule, the spins of the other molecule, spin texture of the other molecules.
I have one more question. Can I ask?
Sure.
So you said that defect levels go below the valence band.
Yes.
So there might be some OJ effects that can take place.
Yes.
Which can still be detrimental for the.
There are evidence of OJ effect. And because that valence, I mean, because defects, as we all know, that in the conduction, in the band model, the defects will be somewhere here above the valence band. But the defects levels are staying there. I mean, it is nothing happening there. Only thing that the valence band is being pushed upward towards the Fermi energy, and leaving the defect states below the Fermi energy, below the valence band. So that's the reason, if the defect states are below the valence band, now they are not taking part. And of course, I mean, OJ effect, I mean, researchers at IIT Bombay, I think they are focusing on this, and they are very much vocal about this OJ effect.
Thank you for a very nice talk. Yeah.
I have a small question. You mentioned that CH3 and NH3 are free to rotate inside the cage.
CH3 NH3 is a single moiety. Yeah, it's a cation. CH3 NH3 plus.
Yeah, you were saying that they are free to rotate inside the cage,
yes.
which you mentioned.
Yes.
So these rotations, will they have any effect or will they have any consequence on the?
Of course, I mean, rotations are important. Again, I mean, this has, again, for this Rashba band splitting, we need that kind of rotation for this, because as such, Rashba band splitting occurs under magnetic field. But here, remember that in this particular molecule, we are getting this band splitting without any magnetic field. And that's, I said about that, why we are getting this kind of splitting even without magnetic field, because of the interesting structure of the molecule, and then remove the center of symmetry, removal of the center of symmetry, and also the spin orbit coupling effect, and also this what is called the rotation of the molecule. So, or rotation of the moiety. So because of everything, we get this kind of splitting without any application of magnetic field, because as such we needed magnetic field to get observe the magnetic the Rashba band splitting. But interestingly,
so the rotations are in the quasi-elastic regime.
Sorry.
The rotation energies are in the quasi-elastic regime of.
I really do not know this one. What is the energy of the rotation?
Okay. Thank you. That was a good talk.
So can we take a few more questions from YouTube chat section? So Ravi is asking, what physics aspect needs to be understood or improved for MAPI?
Like, I mean, this low recombination loss. I mean, of course, we are promoting this Rashba band splitting, but there are other models, and it is still open question that why the material has low recombination loss, because all these effects, these optical properties, the low exciton binding energy, all these things are maybe easier to achieve, but this low recombination loss is very difficult to achieve, and there are many different models researchers are working on. So of course, I mean, that is one direction one can start working in physics aspect. That is, I mean, the origin of low recombination loss.
And Silpi Chaudhary is asking, any other element except SN which has shown potential to replace lead?
Many other elements have been tried, but so far lead remained in the top. Other elements are there. Of course, I mean, combinations are being also used. In different combinations are being used in place of lead. So, but complete replacement has not been achieved.
Okay. Yeah, so we have a question from Professor Nanal, I guess.
Yeah, I had one question. The first comment, a very, very nice talk. I'm completely outside the field and yet I could follow the talk very nicely, and you're really
that is the
covered
success. Yeah, I mean, because it's a cross section of audience, so it's very difficult to make a talk and understandable.
It's very well done. So I had a one general question. You already have touched upon it a bit, but since some of the young students would be listening to it, and this is a topic which is close to almost everybody's heart in terms of the energy generation and so on. So can you give some general advice on somebody who's going to start research in this, that what are the aspects which they could focus on for the solar cell fabrication?
Yeah, I mean, in this particular group of materials, like, I mean, hybrid halide perovskites, a lot of physics answers are yet to be answered. Like, I mean, I said about this low recombination thing, that is really now open, that why we do not completely know that why it is because with this, even with Rashba band splitting, we cannot explain everything. So there can be something else also. So from for a physics student, that is one direction one can research on. And also band engineering for me, I mean, is very interesting because because one should not always work on solar cells, but I mean, that is the materials band properties can be changed by simple solution method, by replacing at the iodine site or at the lead site or at the methylammonium site. That is per se very interesting because you can imagine other devices also. I mean, once you know that, okay, it's very easy to change the conduction band and valence band of the material just by changing something in the solution, and then you get a different Fermi energy or different conduction band, valence band. Okay, let me then try some other devices. Like, I mean, I said about the LED and field effect transistors, but there are other devices like photo detectors, memory applications. So, I mean, once you know the trick of changing the band positions, you can imagine other devices also. So that is my small advice to young students.
So thank you very much, Professor Paul, for really a wonderful lecture. And on a lighter note, I would say you also gave a new meaning to the IPA by bringing an isopropyl alcohol. Since it's very much important in the current era, they should not. Everybody should remember IPA now.
Yeah, no, I really, I mean, took my hand sanitizer with me, and it is based on IPA.
Thank you, Dr. Sahu, for conducting the lecture very nicely.
Thank you very much.
Thanks to all the viewers for joining in. And as Professor Paul mentioned, you can even send an email if you are interested, and please do follow up. I invite you all for the next Saturday lecture by Professor Shikha Verma, and she will tell us about surface sciences. So thank you very much, Professor Paul and Dr. Sahu, and all to you, everybody.